welcome back. Today we're going to talk about mathematical induction, and mathematical induction is a skill that involves using a lot of proofs, a lot of abstract mathematical language. Let me see if I can break this down for you. This is what it means to do mathematical induction. It's a big fancy word that basically just says you're trying to prove a hypothesis is true. Here would be an example. Let's say something happens. It rains on Thursday. Okay, so it rained on Thursday, and you make this hypothesis in your head. You're like, I bet it rains every Thursday. So the next Thursday, you think to yourself on Wednesday, you're like, okay, tomorrow it's going to rain. And the next day is Thursday, and it rains. So the Thursday before, it was true. It rained on Thursday, and you think to yourself, the next Thursday it's going to rain. And so in order for your hypothesis to be true, what has to happen? It would have to rain every single Thursday. And so every single Wednesday, you're looking forward to the next Thursday and you're thinking, okay, this is the day. If it rains tomorrow, then it rains every Thursday. That's the way mathematical induction works. Mathematical induction says, hey, here's a statement about numbers, about a series, about a sequence. And it's true for all the numbers I can think of. So if it's true for all the numbers I could think of, let's just start with 1. It's true for 1, awesome. Then I'm going to say, is it true for all the numbers I can think of in general, like n numbers? Like, does it work for 5? Does it work for 7? Does it work for 9? Okay, good, it works. In order for it to always be true, I have to say it's true for the next number that I would think of into infinity. And the problem with math is there's always a bigger number that you could test, and so you'd be testing and testing and testing. That's why we go to the theory. We say if it's true for 1, and it's true for n, meaning all the ones I could think of, and it's going to be true for the next one, which is n plus 1, then it's got to be true. That's the way mathematical induction works. It's a process. Here's the process. We're going to let S sub n be a statement about the integer n. Okay, so this would be adding up all the odd numbers, or what is the sum of the first 55 numbers, whatever it is, doesn't matter. S sub n is true for all positive values of n if I can prove a couple of things. Number 1, if S sub 1 is true, meaning we're going to show true for n equals 1. Because honestly, if I say it's going to rain every Thursday and it comes up on it's Thursday and it doesn't rain, it doesn't matter. If it didn't work for the first one, it's not a rule. The second thing we're going to prove is that S sub k is true. Okay, so that means it's like it rained on Thursday. The next Thursday that I come up on, it rains. And so then I'd have to have this pattern where it was every single other one. To do that, we're going to show k equals n, right? We're going to substitute in k equals n. And in order to prove that it always works, then we have to show that S sub k plus 1 is true, which means I am going to substitute k plus 1 for n. And there's a process to this. This is what we're going to show. To show this, we're going to show that S sub k plus 1 is equal to S sub k plus A sub k plus 1. What does that mean? Well, it looks like this. If I can show that it rains every Thursday, all the previous Thursdays it's rained, and it rained the next one, that's going to prove that my statement is continuing to be true. Well, really, if every other Thursday it's rained, I really only have to prove, so this is saying every other Thursday it rained. Now I just have to prove it for this one single one, right, going into infinity. So let's look. The process is this. Show S sub 1 is true, assume S sub k is true, show S sub k plus 1 is true. You probably aren't going to remember that right away, but we're going to go through it. So prove that 1 plus 3 plus 5 plus dot 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 plus, this is my A sub k, right? That's my term. And I want to show that that's true for all positive integers n. So 1, prove S sub 1 is true. What does that mean? Well, does 1 equal, because that's my term, right? 1 equal 1 squared. Yes, true. 2. If it works for the first one, then that means that S sub k is true. So 1 plus 3 plus 5 plus dot 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 all the way up to 2k minus 1 is equal to k squared. That's what that means, all right? So that is equal to k squared. So all the way up to 2k minus 1 is equal to k squared. So I want to show S sub k plus 1 is true. So here's the deal. This is how it works, and this is kind of the nuance, the mathematical language. By showing that S sub k plus 1 is true, this is what I'm proving. 1 plus 3 plus 5 plus dot 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 plus 2k minus 1. This right here, this is S sub k, right? This is what I've already seen. I'm adding up every single number in order all the way up to what I've already thought of. This right here, 2k minus 1. And this is equal to k squared. I already showed that. That's already true. But what I need to add to that to prove that k plus 1 is true, plus 2 times k plus 1 minus 1. This is the next term. After n equals k. This is a sub k plus 1. It's saying take that sequence that you already had and add on to it the next one. And I want to show that that's equal to S sub k plus 1, which is equal to not n squared, but it would be k plus 1 squared. Why? Because I'm showing that k plus 1 is true. So I have to sub in k plus 1 for every single value. That's what I did here. This is the sequence. 1 plus 3 plus 5 plus the general term. This is a sub k, as I already wrote down here. So when I want a sub k plus 1, I got to substitute in k plus 1. So it looks a little messy now. Let's clean it up. Really, this part I already proved. This is line 2 right here. So this is already equal to k squared. And this is what I'm doing. Show that S sub k plus a sub k plus 1 is equal to S sub k plus 1. The sequence that I already had plus the next term is equal to the new sequence. So this is already k squared. And what I'm adding to that is simply the next term. 2 times k plus 1 minus 1. And is that equal to k plus 1 squared? This is supposed to be my general formula. Well, if that's my general formula, it's got to be equal to what I already had plus my next term. So let's simplify. K squared plus 2k plus 2 minus 1, because I distribute in this 2. So this would be k squared plus 2k plus 1. Is that equal to k plus 1 squared? Yes. Okay, I showed that it's true with a little bit of algebra. So all I'm adding is, again, what I already had plus my next term is equal to my general formula. So S sub k plus 1 is true. Done. Let's do one more example. This one's a little bit lengthier, so kind of stay with me. 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared all the way up to n squared is supposedly equal to this. N times n plus 1 times 2n plus 1 divided by 6. Show that it's true for all positive integers n. So, number 1, this is a process. Mathematical induction is just a process. So all you have to do is start at the beginning. Show S sub 1 true. So what I'm saying is 1 squared equal to, putting n equals 1. 1 squared equal to 1 times 1 plus 1 times 2 times 1 plus 1 divided by 6. Is that true? Is 1 equal to, so this is 1 times 2 times 3 divided by 6. So that would be 1 is equal to 6 over 6 is equal to 1. So that's true. 2. S sub n is true. So 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared is equal to, now this is where it's tricky, I got to substitute in. It's actually equal to n times n plus 1 times 2n plus 1 divided by 6. Keep your parentheses here. Okay, this is true. 3. Show S sub k plus 1 is true. S sub k plus 1 is equal to S sub k plus A sub k plus 1. This is what I'm trying to show. So S sub k plus 1 would be k plus 1 times k plus 1 plus 1, because I'm substituting in a k plus 1 for all of these, times 2 times k plus 1 plus 1 divided by 6. So that's what it would be if we substituted in k plus 1 for every single one of these. What we need to show is that it's true, or it's equal to S sub k, which we already know. We proved that that's true. That is this. So it's equal to k times k plus 1 times 2k plus 1. All of that divided by 6. Plus my next term. Okay, my next term looks like this. The next term will be this a sub k plus 1. Well, this is always the next term. So plus k plus 1 squared, because that's always my next term. This is my a sub n, right? So that's my next term. And so I'm going to plug k plus 1 into that. Well, okay, check it out. If I rewrite this, k plus 1 times k plus 2, 2k plus 2 plus 1 would be 2k plus 3 divided by 6. This is what it should equal. This is what mathematically, algebraically, putting in k plus 1 to my formula that I assume, that I think might be true, would be. Well, that's equal to what I already had, so k plus 1, 2k plus 1 divided by 6, plus, and this one, I need to have a common denominator. Well, I'll just rewrite it like this, k plus 1 squared. I need to have a common denominator. So what I'm going to do is, I'm going to say this would be 6 times that over 6. Well, take a look. I don't want to work with this side. This is what I'm trying to show that it's equal to this. I'm going to manipulate this side to make it all equal to a single fraction. So here we go. K times k plus 1 times 2k plus 1 plus 6 times k plus 1 squared all over 6, common denominator. Watch this. I actually have an addition up here, but I have a term of k plus 1 here, and I have a term of k plus 1 here. And so what I'm going to do is I'm going to factor that out. K plus 1 times what's left? K times 2k plus 1 plus 6 times k plus 1. 6. So I have got it equal to k plus 1 times all of this in here. So this would be k times 2k, so 2k squared, plus k, plus 6k, plus 6, all over 6. Stay with me, this is just algebra. Well, this is k plus 1 times 2k squared plus 7k plus 6. Now, you may not know where we're going yet, but look, I'm trying to show that this side is equal to this other side. Look how close I am. Really, what I need is, I need to show that this part, because I've got the k plus 1, I'm trying to show that this part is equal to that. Well, when you go to factor this, it factors into k plus 1 times 2k plus 3 times k plus 2 over 6. What did I just do? I plugged in k plus 1 right here. I had my initial formula that I proved, right? My just general s sub k, and then I added to that the next term, the k plus 1 squared, right? That's mathematical induction. Prove s sub 1. Assume s sub k is true. Prove s sub k plus 1 by adding s sub k plus a sub k plus 1. All right, that's all there is to it, guys. Thanks for watching, and we'll see you next time.